Have you ever asked yourself, why does the top balance? Well, you're probably so used to this very remarkable phenomenon that you take it for granted. But look, even when I lean it to one side, it doesn't fall down. It just sort of goes round in a circle. Well, that's because it's actually spinning. You see, if I try to balance it and it's not spinning, it just falls down, and you'd expect that. And once I start it spinning, well, it keeps spinning for a long time. In fact, indefinitely if there wasn't any friction. Now, it's this persistence of spinning motion that will give us the clue to understand the behavior of a top. And our understanding will be based on Newton's mechanics.
That idea, persistence of motion, it reminds me of Newton's first law. Now, Newton's first law says that a free particle will move at a constant speed in a straight line. And another way of saying that is that its linear momentum is conserved. But we want to find a Newtonian explanation for the persistence of the spinning motion of the top. And for that, we'll need to define a new momentum concept called angular momentum. Now, a top is a solid, rigid body, but I'm going to model the rigid body by a collection of particles held in rigid positions by interparticle forces. And to define angular momentum, I'm going to start with the simplest system possible, one particle. Now, to define angular momentum at a given instant, I'm going to freeze the motion like that. Right. Now, the velocity was in that direction. So the linear momentum, m times v, is a vector in that direction. Now, for linear momentum, that's all I need to know, the mass and the velocity. But to define angular momentum, I need to pick some particular point in space as part of the definition. And I'll choose this point here. Now, the position of this particle with respect to this point is given by this position vector, r. And now, I define the angular momentum of the particle with respect to that point as the cross product of the position vector r with the linear momentum mv. Angular momentum is r cross mv. Now, I can't say that's an easy or obvious definition to make. All I can say is that this definition will allow us to derive results that will adequately explain the motion of spinning bodies. So, now let's look at a two-particle system. The position vector is given by r, linear momentum, mv, so the angular momentum of that particle is r cross mv. And the total angular momentum of the system of two masses is the sum of the angular momentum vectors of each of these two masses. And so we can continue. To find the total angular momentum of a system of particles, we sum all the angular momenta of the individual masses that make up that system. So, for a single particle, the angular momentum about a point Q is defined as r cross mv. But a rigid body consists of a large number of masses, of which this is just one. To find the total angular momentum of the whole body, you find the angular momentum of each particle and then add the individual angular momentum vectors together.
Well, this is a sort of top. It's actually just a bicycle wheel spinning about its axis. Now, Paul has told me in order to understand its motion, I've got to discuss its angular momentum. Now, to do that, I'm going to start off by using a model. I'll model it by a disk spinning about its axis. And in order to see what's happening, what I'll do is I'll cut the disk open and see what's going on inside. It's spinning this way around the axis, and I want to calculate its angular momentum. Angular momentum with respect to this point. I can do that by finding the position of the particle. So that position vector is r. Right. Now the momentum of the particle, well, it's instantaneously going in that direction. So it's mv. Let me get that in here. And r cross mv is the formula for the angular momentum of that particle. Well, I can calculate that by using the vector product rule. But it's easier if I have my little device here, which in fact is a triad, which will automatically give me that vector product. If this is r, and that's mv, then this third vector is r cross mv. And I use that by positioning it correctly on my particle. So, R is along the position vector, mv is the momentum, and this rule tells me R cross mv is a vector along here. So this is the angular momentum associated with that particle. Well, because it's a symmetrical object, there's another particle here going round in this direction, and that has position vector R, and that's got momentum in this direction, and the same rule will tell me R cross mv is a vector along here. So its angular momentum vector will actually be in this sense. So now we see the contribution of these two particles gives me two angular momenta, and by vector addition we can see it's going to give me an angular momentum along the axis. Well, that's just a calculation for these two particles, but because it's a symmetrical object, we can actually do the same thing for all the pairs of particles making up the disk, and then we'll get the total angular momentum vector will be along the axis of rotation of the disk. So the angular momentum of my spinning bicycle wheel is a vector along this direction, and it's a constant vector. It's pretty constant direction and pretty constant magnitude. Now, if I lean it, well, you can see that it's no longer constant. The angular momentum vector goes round, it precesses. Well, I'd like to know when is an angular momentum vector constant and when is it going to change?
So, to discover what causes the angular momentum to change, I'm going back to the simple one-particle system again. Now, the angular momentum of a single particle about a point Q is given by R cross mv. Now, to find out what will make it change, let's look at the rate of change of angular momentum. And let me differentiate it like this. And the second term. Now, this first term is just equal to R cross F, because from Newton's second law, force equals rate of change of momentum. And this second term is just V cross mv, and that's always zero. Right? The cross product of parallel vectors is always zero. So it's this term, R cross F, that will make the angular momentum change, and we call R cross F the torque applied to the particle. Now, the angular momentum is defined with respect to a given point, and so the torque will be defined with respect to that same point. And the rate of change of angular momentum equals the torque. Now, for a system of particles, we have the total angular momentum equals the sum of the angular momenta of the individual particles. And to find the rate of change of total angular momentum, we have to sum the contribution from the individual particles. Now, this sum I can get from this equation up here. Right? It's just a sum over the individual particles of the quantities Ri cross Fi. Now, the force on the ith particle can come from two types of sources. External sources, that is, like gravity, and the other particles that make up the system, interparticle force. Now, we've shown in the text that if the interparticle forces obey Newton's third law, then their net contribution to the total sum is zero. We can just forget them. So, the rate of change of total angular momentum is equal to the sum of the torques on the individual particles that are produced by external forces. And that is equal to the total applied torque. Now, we've derived this result from Newton's second and third law. And this equation will allow us to explain the behavior of spinning tops as well as a host of other applications involving rotating bodies.
So, according to Paul, and Sir Isaac Newton, this behavior is caused by the action of torques on the spinning body. In order to find out what torques are present, let me go back to my model. So, what forces are present, first of all? Well, there's the force of gravity, and according to the correspondence text, that force produces a torque which you can calculate as if it were due to the weight of the disk acting from the center of gravity. And that's got position vector r. So that's one torque. By the way, there's also a force at the point of support. But as the point of support is the one about which we're taking our angular momenta, then its position vector vanishes, and that does give a zero torque. So the only torque is the one due to gravity. And it's r cross f. Now, my vector product rule, and I've got a little triad here, it's not an orthogonal triad this time, will tell me that r cross f is just a vector gamma in that direction. And so, on my disk, it will give me a vector like so. Now, according to my angular momentum equation, this is the rate of change of angular momentum. And so that tells me that the angular momentum vector is going to change along the direction of that arrow. So instantaneously it goes around like that. But at the next instant in time, the torque is still in the same direction, so the angular momentum vector still changes in the same direction, and it moves around a little bit like that again, and so on. So the net result of this is that the angular momentum vector precesses, it goes round in a circle. And that's precisely what we see happening. And this also explains why top balances in the vertical position. You see, when the axis is vertical, the force of gravity is parallel to the position vector. And so the net torque is zero. And that's why the top balances. In fact, this position is even stable, because if I displace it slightly, it doesn't fall over as it would do if there was no spin, but it actually goes into a precessional motion. Well, tops are all right for qualitative tests of this equation. But if we want a precise quantitative test, then we really ought to go to a more precisely engineered object. And such an object is the gyroscope. Well, here I have a gyroscope. It's just a heavy wheel which I can make spin about its axis, and when it does, it gives me an angular momentum along the direction of the axis. And it's very cunningly mounted so that it's actually free to turn in any direction. Now, here I've got a second gyroscope which is actually spinning, and so it has an angular momentum vector in the direction of the arrow. Now, I can do some experiments with these gyros. The first experiment, supposing I were to put a weight on the rim of this gyro which isn't spinning, what happens? And of course, exactly what you expect. The weight's going to fall off. Now, what happens if I put a weight on the rim of the gyro that's spinning? Well, in fact, not only does it not fall off, it precesses slowly in that direction. Now, if I put a second weight here, it stops precessing. Well, these phenomena I always find amazing, because there's no way my intuition would predict what's going to happen. And if I put twice the weight, still doesn't fall over, just goes round twice as fast. Well, I say I can't predict intuitively what's going to happen, but I have my angular momentum equation, so I can actually predict analytically what's going to happen. And I can do this by using the equation the following way. The way the gyroscope is mounted, there is no torque about the point of interest, which is the center of mass of the gyro. So that's the point about which I'm going to take my angular momentum. Now, by adding a weight to the rim, I'm actually adding a torque. So all I have to find out is in what direction the torque is going to act. Well, I've got a weight here with some arrows on, and I'll explain what these arrows are. If I place this weight on the rim, this arrow is the position vector r, this is the force of gravity, And R cross F is the direction of the third arrow, and that's the torque. So according to my equation of motion, the change of angular momentum must be in the direction of the torque, which it is. So that explains why the gyroscope is precessing in that direction. And furthermore, I can understand why, if I put 2 weights down, it precesses twice as fast. The answer is the torque is twice as much as before.
Now, that's the principle of the gyroscope. A heavy spinning wheel produces an angular momentum vector with large magnitude. And applying a torque to the gyroscope produces a corresponding rate of change of angular momentum. Now, we can look at this equation the other way around. We can force the angular momentum vector to change, and then measure the rate of change of angular momentum by measuring the applied torque. And we can do that with this apparatus over here. It is a beautiful big gyroscope, and it's fixed on this table so that I can make it rotate in this direction. Now, the bearings are loose in this direction, and the springs will supply the corresponding torque. Now, we're going to do an experiment. We're going to spin the gyro up like this, so the angular momentum is in this direction. And then we're going to rotate the wheel like that. Now, let's try to predict whether the springs will be stretched or squeezed. Well, the angular momentum is going to change in that direction. So that means there has to be a torque in that direction. And we're measuring our position vectors from the center of the gyroscope itself, out to the spring. So that's R in that direction, and R cross F in that direction. That means a force has to be vertical. And that means that the spring must be stretched. Okay? That's my prediction. So let's try it out. I'll start the wheel up. And it's a good heavy wheel. And now, rotate the turntable, and the spring reacts just as predicted. And the faster the rate of change of angular momentum, the greater the required torque. So we can measure the rate of change of angular momentum by measuring the extension of the spring. It is this principle that is used in many practical devices. And the device we've chosen to exemplify this use of a gyro is a ship's stabilizing system.
This is the ship we're going to look at. It's a cross-channel car ferry. The stabilizers which prevent the ship rolling are just these fins. There's one on this side and one on the other side. Now, these fins are airfoil in cross-section. They can be tilted up and down. In this position, the pressure of the water passing the fin creates a force downwards. Tilting the fin the other way creates a force in the other direction. Waves passing across a ship cause it to roll from side to side. The stabilizers create forces to prevent this rolling. When the waves are forcing the ship in one direction, the stabilizer fins must be angled to provide forces to counteract it. The control mechanism for this system must be sensitive to the rate of change of roll angle of the ship. And you've probably guessed it, it's going to involve a gyroscope. So, Paul went down to Dover to look at this gyro fin stabilizer system.
The fins are about 4 meters below the surface of the water. And at the moment, here in port, they're tucked away against the side. The controls, well, they're way up on top, on the bridge. But our first call will be to see the gyro fin roll sensing equipment down in the engine room. This is the engine control room, and it's here that the ship's crew monitor every aspect of the ship's operation, including the gyrofin system. Now, the control unit is right down at the other end of the console. And here it is. Up here we have electronics, a computer. The part we're most interested in is the gyro, and it's down here. That green case with the knob on top, that's the thing. Now, if we took that case off, we'd see a unit that looks very much like the unit we've got over here. Now, the spinning wheel is inside that black case, And it's kept up to speed by making it the rotating part of a motor. It maintains a constant rate of rotation and therefore a constant magnitude of angular momentum. You can see the axis of the gyro right there. And it's aligned across the ship. And it'll be forced to move with the rocking motion of the ship. So let's simulate the rocking motion of the ship. As the ship rocks back and forth, the angular momentum is forced to go down and up. The gyro twists against springs, which provide a torque which is proportional to the extension of the springs. So, by measuring the extension of the springs, we measure the torque that's induced in the gyro. That torque is equal to the rate of change of angular momentum of the gyro, which is proportional to the rate of change of rolling angle. So to have another look, and to see that it's really a gyro that's at the bottom of it, let's have a look at our studio gyro. Now, the gyro spinning in this direction is the angular momentum pointing this way. Now, I'll force it to precess, up and down, up and down. Now, with the angular momentum changing in the vertical direction, there is a torque in the vertical direction, which produces a sideways motion on the gyro, which is recorded on the springs. And you can really see that is the rate of change of roll angle that I'm measuring, not the angle itself. No matter what angle I leave it at, the gyro always rights itself. So that's how the gyro part of the system works. And it measures the rate of change of roll angle. All that remains is to see how the gyrofin system works in practice.
Clear all round, arms, all clear.
Only when we're clear of jetties and in deep water can the stabilizing fins be put out. Below decks, it takes massive pistons to let out the fins. Each assembly weighs 25 tons. When both fins are out, a control piston adjusts the angle of each fin, up and down. At the moment, the sea isn't very rough, so the fins only need provide small amounts of lift. But they respond in a split second to provide the lift demanded by the stabilizer system. Here on the bridge, we can give you the evidence of the way in which the gyrofin system is working. The measure of that lift demanded from the control circuits is given on this meter here. Now, another part of the control system is actually measuring the lift that is provided by the fins. This meter here shows the amount of lift given by a fin, and this is the angle of the fin that gives that lift. The control mechanisms continuously balance demand against performance. And at the heart of the system that computes that demand is our old friend, torque equals rate of change of angular momentum.